All right, so we are just going to continue here, and we are going to develop a mathematical model for the traveling salesperson problem, and our objective is just going to be finding the minimum distance, the Hamiltonian cycle for a complete network. Now, the parameterizations of the mathematical model is very easy because there are only a few sets of parameters here. So what are the sets of this problem? The sets that we are going to consider is just, there's a single set, the set of all nodes in the network. Okay, so we have lowercase n cities in our network in a sequence to visit, okay, in a cycle to visit, and capital N represents the set of these cities, okay, set of the nodes in our network, and the cardinality of capital N is equal to lowercase n. So cardinality means the number of elements in set capital N. Now we are going to define our parameters or notation of our parameters. So the only information that we require is the direct distance matrix. Okay, so given the set of the locations in our network diagram, we need to have the direct distances between every couple of city from node I to node j. Of course, we assume that the bidirectional distances are the same. So if Cij represents the distance from node I to node j, Cji will also be equal to Cij value basically. Okay. Now, since we are going to define the direct distances between every couple of nodes, we should say that I can change from 1 to n and j can change from 1 to n. Of course, in this distance matrix, we will have some diagonal elements as well. Okay, so we assume that the distance of a city to itself is simply 0. However, we would like to prevent stalling in a city, therefore we will assume that since there cannot be any direct route from a city to itself, we will assume that the direct route distance from a city to itself on that distance matrix is going to be the capital M value. Okay, so it is not going to make a difference in the end, but just for us to understand better, there is not a direct route from a city to itself. Therefore, we can introduce a huge penalty cost there just to ignore this value in the distance matrix. Okay, so this is the only parameter that we need to consider in our problem. Okay, only the direct distances in our complete network, and we have the set of cities or the set of nodes. Okay, now what is the thing that we are deciding here? Okay, so basically, whenever we are in a city I, let's just say currently we are in city I, node I, the decision that we need to make is the next city to visit, right? So which node J I am going to visit next? So what is the next city in my visiting sequence, visiting order to visit? Okay, so I'm going to ask this question for every next city. Am I going to visit city 1 now? Yes or no? Or am I going to visit city 2 now? Yes or no? Am I going to visit city 3 or not? Yes or no? So I'm just going to make this decision for every city. Of course, I'm just going to give a single yes answer. The other answers will be no, right? So if there are 5 candidate cities to visit in the next, okay, after this current city, I'm going to answer this yes or no question for every 5 of them, but only one answer is going to be yes and the other 4 answers is going to be no. Okay, so I'm not deciding about the next city to visit. I am answering the question, which is a yes or no question. Am I going to visit the city next or not? And I'm going to answer this question for all potential next cities. Okay, next cities to visit. Okay, so we are going to use that analogy to define our decision variable. Xij represents a binary decision variable which indicates if node j is going to be visited after node I. Okay? If we are going to visit node j immediately after node I, then xij binary decision variable will be equal to 1. If not, it is going to be equal to 0. Okay? Or in other words, now you see this is a Hamiltonian cycle, right? In this Hamiltonian cycle, there are there are edges which are used on our cycle and they are indicated with blue, and there are edges which are indicated by dashed lines, which means these are not used in our Hamiltonian cycle. Now, if an edge is used over the Hamiltonian cycle, just like these blue edges, they are called to be active on the Hamiltonian cycle, active. So they are being used. And if edges are not used on the Hamiltonian cycle, then they are called inactive. They are not being used. Okay. Therefore, we also can explain Xij as an indicator that shows the direct route or the edge from node I to node j is active if that binary variable is equal to 1, active on the Hamiltonian cycle. Otherwise, if xij is 0, we say that this edge is inactive on the Hamiltonian cycle. It is not active. Okay, it is not used on the Hamiltonian cycle. The edges on the Hamiltonian cycle are the active edges. Okay, so basically, we need to develop such a model. We are just going to run a double summation over indices I and j, and we say that if edge ij is active on the Hamiltonian cycle, then Cij of units of distance will be contributing to the objective value. If edge ij is not active, then that distance will not be traveled in any way, therefore it will be multiplied with 0. So we are going to run this summation for every edge that exists in our complete network. So we are going to do this for every couple of nodes in both directions, basically. Okay. Now, if an edge is active from I to j, of course, it may not be active in the reverse direction. Xji is not going to be active, of course, but this is just going to be determined by the optimization model itself. Okay. So what are the constraints here? My second set of equations here gives me the first set of constraints. As you can see, for a fixed next location j, okay, we should say that in this problem, we should only come to that location j from one city, okay? So if you are going to visit a certain city in the Hamiltonian cycle, and obviously you are going to visit everywhere, okay? Let's just say you are going to visit city j. To this city j, you can only arrive there from one city which is visited previously, okay? So this means what? Among all cities from 1 to n, if you are going to visit the next city j, you are going to be visiting there only from one location. So which means for all edges which are incoming to the j location, only one of them can be active. Okay, so you can only come or arrive to a certain city from a single city. This means among all edges which are incoming to the j location, only one of them can be active. Therefore, this summation from I changing from 1 to n, the summation of xij values for a given j location should be equal to 1. And this is obviously going to be true for all cities, right? So for all cities j, only one of the incoming edges should be active. Similarly, for all cities I, okay, for any city I, one of the outgoing edges should be active. So if you are currently in location I, city I, as a next city, you can only visit one of the cities as a next city. Okay? When you choose, I mean, you cannot go two places simultaneously, as you cannot come from two places simultaneously. So this means when you are in city I, only one of the outgoing edges can be active. So you can only choose one place to visit as the next city. This means for given I, a summation of xij values as j index changes from 1 to n should be equal to 1. And this should also be true for all cities again. Okay? So the second set of constraints tells us only one incoming edge can be active for a given city j, and the third set of constraints says only one of the outgoing edges can be active for a given city I. Okay? Now, sometimes we may think that when we write these two constraint sets, plus obviously the binary constraints of xij values, sometimes we think that it is sufficient. It is sufficient to create a Hamiltonian cycle with these constraints. My friends, this is not true, unfortunately. So we have the Subtour situation here. Okay. Now you see, when you think about the second set of constraints and the third set of constraints here, these sets of constraints are satisfied in this feasible solution. But this feasible solution is not a Hamiltonian cycle. Okay? So this solution is feasible. Let's just imagine you have 9 nodes in your network diagram. So as you can see, every node has a single active incoming arrow and single active outgoing arrow. Okay, this is true for all nodes in our network diagram. Every node has a single incoming and single outgoing arrow. But this is not enough to create a Hamiltonian cycle, because Hamiltonian cycle is a single cycle. We have two cycles here which are distinct from each other. Therefore, in this solution, we are not basically starting from one point and visiting all cities exactly once and coming to the first one. So this is a solution which has two subtours. Okay, so we have two subtours in your feasible solution. So we need to write a subtour elimination constraint in our model. Okay, so this solution, even though it is feasible for the second and third set of constraints, it is not a Hamiltonian cycle. It is not a feasible solution for the traveling salesperson problem. So how do you create a subtour? Okay, now I'm sorry, how do you eliminate a subtour? So let's see. Imagine this subset. Okay, so in this feasible solution, imagine this subset which contains the first, second, and the third nodes. Now, if there are 3 edges active in this subset of nodes, obviously it will create a subtour, right? Now, for a given subset in your network, subset of nodes, let's just focus on the second subset here, 4, 5, 6, 7, 8, 9, 10. 8, 9, okay, 9. So you see there are 6 nodes here, and in this, among this subset, we are seeing 6 edges again. So given a subset of 6 nodes in your network, between these 6 nodes, if you see 6 edges, obviously there will be a subtour. Okay, so what is the rule here? For any given subset, of the nodes, in your network, so you are just selecting a bunch of nodes as a subset. In between these nodes, if the number of edges is equal to the number of nodes in that subset, obviously there will be a subtour in that subset. Okay, so we are saying this for any subset of the node sets. Okay, for any subset except the empty sets. Of course, empty set is a natural subset of every set, so we are not going to think about that. for, let's just say, any non-empty subset of the node set. From this subset, from the nodes in the subset again to the nodes in that subset, the number of active edges in our Hamiltonian cycle is less than or equal to the one less than the number of nodes in that subset. In that case, there will not be any subtour in that node, in that subset, basically. So imagine this situation, okay, in this network. You can choose any subset of the nodes here. Let's just focus on this 1, 2, and 3 nodes, okay? Let's just focus on these 3 nodes. Now, just considering these 3 nodes, in between these 3 nodes, how many active edges we are seeing? Only one, right? So this edge, this node is not connected to that node. This node is not connected to that node. Only this node is connected to that node. So for a given subset of 3 nodes here, we are only seeing one active edge. Okay. Now imagine these 5 central nodes: 1, 2, 3, 4, and 5. Now, in between these 5 nodes, we are only seeing only 4 active edges. 4 active edges, right? If you activate one more edge, then it will create a subtour, right? In any way you are drawing this 5th edge, it is just going to create a subtour. Therefore, we should say that for any given subset of the nodes, the total number of active edges within the subset of nodes should be at most one less than the number of nodes in that subset. Okay, so this is the first type of subtour elimination constraint. Okay, we are going to develop another model, another integer programming model for the traveling salesperson problem after this one. You will see that it is also possible to eliminate the subtours with that constraint. But here's the thing, my friends. What is the unfortunate situation here? Now imagine this. If you have only 10 cities to visit, 10 cities to visit in your Hamiltonian, in your complete network. So you are just going to create a Hamiltonian cycle for 10 cities for the traveling salesperson problem. Now you need to write this constraint, subtour elimination constraint, for all subsets. And we know that if you ignore the empty set, we have 2 to the power 10 minus 1 subsets for the network. Okay, the network for 10 cities only. So what is 2 to the power 10? It is 1024. And if you eliminate the empty set, it will make 1023 subset. Maybe you can also eliminate the sets in which you only have a single element. Again, it will reduce the number of subsets here, but still there's still a large number of subsets we have in a network of 10 cities. So you see, depending on the size of the network diagram that you are working on, the subtour elimination constraints that you are going to write with this representation is just going to increase exponentially, as 2 to the power n represents the number of subsets in a set that has capital N, I'm sorry, n elements, okay, n cities. So it is just going to be 2 to the power n, lowercase n, of course, 2 to the power n subsets that you are going to create. Now, here's a good situation. Even though the number of constraints that you need to introduce grows exponentially here, you are not going to write all subtour elimination constraints for all subsets. Okay, so as you can see, in a Hamiltonian cycle of a network with 9 cities or 9 nodes, there will be exactly 9 edges active, right? 9 edges active. So you see, I have a network here. I have a subtour here, And whenever I have a subtour in one subset, in the complement of that subset, I observe another subtour. I necessarily observe another subtour. Okay, it is actually a necessary requirement. So if there's a subtour in the complement of that subset, there will also be a subtour. Okay, now if you do not have a subtour in a subset, in the complement, also the subtours are going to be eliminated. But this can only be true for every subset, I mean for all required subsets that if you write this subtour elimination constraint. Okay, for example, if you write the subtour elimination constraint for subset 1, 2, 3, the subtour elimination constraint will automatically satisfy for the subset which is the complement. Okay, so if you write the subtour elimination constraint for 1, 2, 3, so let's check the subtour elimination constraint here. We say that within this subset, for all possible edges, we should only activate at most 2 of them. So the cardinality of the subset is basically 3, and 3 minus is 2, 1 is 2. So this means among all potential edges that we can create between 1, 2, and 3, only 2 of them at most can be active. So we say that x12 plus x13 plus x21 plus x23 plus x31 plus x32 should be less than or equal to 2. Okay. Now, if this constraint is satisfied, and if you write this for all possible subsets again, for the complements, it is also going to be satisfied as well. Okay. So if this constraint is satisfied, you will see that the subtours will be eliminated for the complements as well. Now, if you write this constraint, of course, you may think at this point, if I write this constraint only, it may be possible to create a subtour in the complement as well. Yes, that is true, but I am not saying this. Please be careful. I am saying that if you write this constraint for all subsets, for the complements, it is automatically going to be satisfied. Okay? So what you are going to do is this. You are just going to determine half of the subsets. For the other half of the subsets, these are going to be automatically satisfied if you simply write these constraints for the half of the subsets. Okay? Now, the other half should be the complements of the constraints for the subsets that you are going to write the constraints for. Okay, now you are going to understand this better in the explanation, in the example. Okay, so I have a set of 5 cities to visit. Okay, this is a very small size network. In fact, you can immediately find the optimum solution by trial and error, because you do not have too many feasible solutions here. Remember now, n minus 1 factorial over 2 here. So we have 5 cities. 4 factorial is 24. 24 over 2 is 12. So there are 12 possible Hamiltonian cycles that you can draw in this small size network. So you can make a list of these and identify the shortest one easily. Okay, so we have 5 cities to visit, and we need to develop the mathematical model for this problem. Our objective function is basically the distance matrix times the piecewise multiplication of the decision variable matrix. So we are going to multiply the corresponding binary decision variables that belong to each edge in every direction with the regarding distance. So we multiply x11 with big M, x12 with 31, x13 with 56, so on and so forth. So I have 25 decision variables in this model for 5 cities, and this is just going to be my objective function to minimize. Now, the first constraint set tells me that for city 1, as you can see, the first constraint, I can only arrive to city 1 from one city only. Okay, only one of the edges, x11, x21, x31, x41, x51, is going to be active. Similarly, I can arrive to the second city from only one of the cities. So only one of the edges 1, 2, 2, 2, 3, 2, 4, 2, and 5, 2 is going to be active, so on and so forth. So these first 5 constraints indicate that to each city we must arrive exactly once. And the constraint set 3 here indicates that from each city we must depart exactly once. Okay. So this means from city 1, we can only activate one of the edges, 1, 1, 1, 2, 1, 3, 1, 4, and 1, 5. Of course, 1, 1 edge does not exist. And in fact, it will not be activated due to the big M coefficients in front of these diagonal decision variables. And again, there's a misprint here, my friends, unfortunately. X1 for, X2 for, X3 for, X4 for, and X5 for this must be just like in the X3 for, I'm sorry, yes, X4 for and X5 for, yes. So it must be, so I need to change these two indices. These are misprints as well. So the diagonal elements are just going to be ignored due to the objective functions coefficients. And here, the second and the third set of constraints are easy to understand. They are just indicating that to each city we must arrive exactly once, not at least once, exactly once, and we must depart from each city once. But this is not enough to create a Hamiltonian cycle. Again, as I have said, for each subset of the network, we need to write the Subtour elimination constraints. Okay, so remember the Subtour elimination constraint. Again, here we say that for a given subset of nodes, any subset of nodes except the empty subset, the total number of active edges within that subset from nodes to nodes in that subset should be at most the cardinality of that subset minus 1. Okay, so for example, let's do that. Imagine subset 2, 5. So we are only considering 2 edges. So in this subset 2, 5, there are 2 edges, 2 to 5 and 5 to 2, right? So we have 2 edges here, 2 to 5 and 5 to 2. Only one of these edges should be active, right? If 2 of these edges are active, then there will be a subtour from within 2 to 5, right? So we visit 2 after 5 and 5 after 2, if there are 2 edges active here. Now, in order to write that constraint here, we should write that among the edges within this subset 2, 5, x2, 5 plus x5, 2, so this one, only one of these 2 should be active. Only one, at most, by the way. Okay, we are saying that maybe none of these 2 edges will be active in the optimum solution. So we are saying that in a subset among the active edges, the number of active edges must be at most cardinality of that subset minus 1. The cardinality is 2. There are 2 elements here. 2 minus 1 is 1. So this means x2 5 plus x5 2 should be less than or equal to 1. Now, I am going to write these Subtour elimination constraints for all 2 element subsets, all single element subsets, and for the empty subset. Now, we do not need to write the empty subset Subtour elimination constraint, obviously. Now, here's the thing. If you write this Subtour elimination constraints for these 16 subsets, for their complements, the Subtour elimination constraint will automatically be satisfied, my friends. Okay? But I'm not stating that. If you simply write the Subtour elimination constraint for a single subset 2, 4, that does not require for the complement, it is also going to be satisfied. Okay? Unfortunately, we need to write this for a half of the subsets, okay? Such that the other half will be the complements of the first half, okay? So if I write this constraint for 0 element, 1 element, and 2 element subsets, then 3 element subsets, 4 element subsets, and 5 element subsets will be automatically satisfied, okay? Now, you do not need to write any Subtour elimination constraint for a 0 element subset, for empty set. You do not have to write it for single element subsets because they will be redundant, because the edges within a single element subset are only the edges. Consider the edges uh, which is routed to the node itself, right? x11, x22, x33, x44, and these are automatically going to be equal to 0 by the objective function. So these constraints will be redundant because the right-hand side values will be 0 because the number of elements in the subsets minus 1 is 0. Now we are going to write constraints starting from two element subsets here. And for this small size instance, if you just write these constraints for two element subsets, automatically three element subsets, four element subsets, and five element subsets, Subtour elimination constraints will be satisfied. Okay, but again, we do not need to forget about the binary constraints in our mathematical model as well. I hope that you understood the integer programming model that we developed for the traveling salesperson problem. So this Subtour elimination constraint is not very hard to understand. You need to write this for every subset existing or not. However, as I have said, if you write this constraint for a half of the subsets that exist in your network such that the other half is the complement of the subsets that you are writing the constraints for, you do not need to write the constraints for the other half. Okay, they are going to be automatically satisfied. This is reducing the number of constraints that we need to write, but still if the size of the problem increases, if the number of cities increases in your network, the number of constraints that you are going to write will grow exponentially. Therefore, this is not a friendly model that we can develop for the traveling salesperson problem. So what we are going to do is this. In the next video, we are going to develop another integer programming model for the traveling salesperson problem, which is a little bit complicated to understand, but the number of constraints that you are going to end up with in this model is just going to be less than the first integer programming model for large size problems.